Hi everyone. So I'm Bofu from Austin Consultants, and today I can talk about the hidden Markov model in LabVIEW. So firstly, the outlines I'm going to talk through. Firstly, what is hidden Markov model, and how to build one yourself, and like the implementation of hidden Markov model in LabVIEW. So what is hidden Markov model? According to Wikipedia, it's a statistic Markov model in which the system being modeled is assumed to be a Markov process with unobserved states, i.e. hidden states. So it is basically it's a Markov model, but hidden. That's why I put in this picture. But so a Markov model is you can imagine it as a state machine, but the way to transfer to the next state is not depends on the action you perceive, but it's in a probability, and there is a assumption that the probability goes to the next state is purely on its previous states or states. So in a very extreme simple case, we just assume the next state, the probability going to the next state is depending on the previous one state. That is called a one-order Markov model. And so, assuming, say you have 3 dice, and you pick up. So you have different dice. So for this one, you got 6 faces, and 4 and 8. You're picking up different one, and the way you pick up the next one is depending on what the current one you're using, and like the probability might totally according to different people got different habits. And now assume that you can't see what die you picked up, but you can only see the number, like after you throw it, the number that fits in the top. So in this case, for the first die, you can see 1 to 6, and 1 to 4, and 1 to 8. So there are 2 assumptions. One is the next state is determined by the previous state, and the next one is all the visible states is determined on the hidden states, i.e., like the probability using 1. Is 1/6 if you're using the first die, and 1/4 if you're using the second die. So if we draw it in a sort of state machine way, is we got 3 dice, and well, I didn't draw all of them, but 8 numbers, and you got different probabilities go from one hidden state to the visible state, and also different probabilities go to the next state. So what's the use of this complex model? Well, it's widely used in speech recognition and written recognition. So for example, when you hear something, when you hear people saying a sentence, the way you want to like transmit that to text, the signal you have got is analog signal, is waveforms, and you chop that into different words, but probably people just say it slightly differently for the same word, and the way the different words combine are following some probability. So you can't really see what they are saying because you don't see the text, but you can hear the visible state, i.e. the sound. So considering like there, like when you say there can be 2 words. It's over there as it's their product. And it's according to what they said previously that you give you the information of what that is. And another, and also like writing, because people can just write. If you just look at a single letter, it can look like everything, like S or 5. But it's also like using the previous letters to determine what the next one is. And bioinformatics. In some applications, there are people try to sequence the genes. So the genes are following to the previous genes under different probabilities, and you can't really see the genes, but you can see the pretend they expressed. So to turn this model into a mathematical model, firstly, we need a transition matrix, i.e. the probability to transfer from one hidden state to the next hidden state. Take the weather, for example. Say today is raining, and the probability for it to maintain raining the next day, say it's 0.3, and it is sunny, and it's 70% to be sunny the next day. And if today is sunny, you've got different probability as well. We can turn this to a table. So you've got current state and the next state. So you've got a matrix here. We call this transition matrix. And the emission matrix is this one. So the probability from one hidden state to different visible states. So in this case, everyone is 1/6 and 0 for 7 and 8. So 1/4 for 1 to 4 and 0 for the rest. So 1/8 for all of the numbers. So back to the weather example. So say if we put a seaweed, say if we can't really see what's the weather like outside, but instead we put a seaweed, then the seaweed might be dry. Well, there's 10%. It is dry when it's raining, and 0.3 is soggy, 0.6 when it's raining. You've got another matrix. We call this emission matrix. Also, to enter into the state machine, there is an initial state. So that one is called initial state. We use pi to stand for that. So for one hidden Markov model parameter, you need 3 metrics. Or the last one is a vector, really. So transition matrix, emission matrix, and initial state. Now, how to build one hidden Markov model? For a hidden Markov model, you're always trying to solve three kinds of questions. One is evaluation, decoding, and last one is learning. So what are they? Evaluation, say, so you have the dice, and you just throw different dice, a lot of times, and you observe the numbers. So you got a sequence of numbers, and you want to figure out the probability of that one, or the probability of the next number. And in a real case, this is used to evaluate like which module you took use of. Because, for example, I just follow my own habit to pick up different dice, and another person might just follow different probability. So rather than you can really see which dice the person is using, you just observe the sequence of numbers. You can predict like which one behind it was really throwing the dice. So in a mathematical way, it's given the model, so you know the probability of everything, and you can see the visible states. Now try to figure out the probability. This is solved by using forward-backward algorithm. I will just give you a very brief explanation of that. So to figure out the probabilities, since we got the matrix, so we can just try to basically do the multiplication. Basically, it's A multiplied by B for state 1, and multiplied by A2 multiplied by B2. It's really like following different paths. Say you got state 1, so you got visible state 1 to T. Now you are trying to figure out, calculate all the probability or all the paths allows you to go from the initial state to the last state, and then you sum up all the probability. That is a naive way of doing this, but considering the computation power, it's a lot. So, because in real case, you always like easily get thousands of sequence. So it's a very long sequence, and if you want to do the, say, you got like 3 different combinations multiplied by 3 by 3 by 3. So it's just a lot of computation.
Okay.
So instead of doing that, we do the sum of the previous states. So rather than every time you're calculating a new routine, you can assume, say, that is the last one. You calculate the previous one or the previous 2. Then for the next one, you just start from this. So it's doing it in an iterative way. So you can do this in a forward way. So you start from the initial state and calculate the so you calculate the probability, go to the next state, and also multiply it by the probability of showing a particular visible state. You do the sum, and then you store the number or store the values in the temporal variables. Next time when you calculate the next state, you just start from this one. The next question is decoding. So now you got the model, and you have seen the visible states. So what really happened? What happened underneath? So back to that dice problem is, so which die you pick up every time? Which is most likely die you pick up? This, when you are figuring out the speech recognition one, is so which word you're really saying. We heard the sound, we heard the sound wave, but which word you're saying underneath? That's the problem you will try to figure out. Again, so that is back to the path problem. It's trying to figure out a path, give you the most probability. So to start from the initial state and end at the very last state, you try to figure out the path with the maximum probability. That is an NP problem. You have to figure out all the probabilities and to find out the biggest one. So again, that is hard. Another way to address this is if one path was optimized and it say go past ST, so some state in the middle, all the rest are optimized as well. So say that is the final state, and if it is the optimized path went past this one, all the rest have to follow the best one. So, otherwise, there will be a better path than that. Then that is not the optimized node you pass through. Is that intuitive? Well, that allows us to say, so from the beginning, we're always trying to find out the path, the node that gives us the best probability.
You get messed up a bit if, say, somebody has used the wrong terminology for like the word there, for example.
Yep.
So you're trying to get the best probability, so but you would possibly still lose what their meaning was when you did it, or
you.
Full state there.
So if you want to figure out what their word really is, you try to. So you have the previous hidden Markov model, i.e. the probability to connect one word to another. And then the previous one, if it is they, there might also be different words of they, but one can be really they are. So they, why they, sorry. It is, say it is. And then you are, after basically it's figure out is, gives you more information to figure out what the next one, what the next word is.
So
does it make sense?
Is it trying to pre-guess what the next word would be?
That's one way. You can pre-guess it, but also it's given you heard the sound there.
Yeah.
You try to write it down. What that word really is. Is that there, there, or is here and there.
So, in terms of the hidden part of the kind of Markov model, would a normal Markov model you just have the information for what part would be the hidden in a sentence?
The real meaning is the sentence, or if you write down each word, if you write down the words are the hidden states. But we are saying that there's no subtitle, so you don't know what you're really saying. I know what you're really saying.
Yeah.
So I just hear the sound is the visible states.
Okay.
Okay, so I'll try to recap a bit. So the previous, so back to this is, if you say a long sentence, what's the probability? Well, what's the probability of that sentence could be?
So you're saying the longer the sentence is, the higher the probability that you get that right.
The more previous information you got.
Yeah.
Yeah. So say the current word. Well, for this model, for the current word, the very first word you said doesn't really give the information of the very last word, but it can give you more information of the second word. So which just pass through, and so you can be more confirmed on the previous one. So now you see what it's saying for the last one.
Sorry,
Yeah.
so if you say there was a word there and you had like the previous word was over there.
Yeah.
So then that could still be either. So if you had the whole sentence, so we are going over there, it's much more likely that it's THGRE, but it could still be we are going over their heads, so then we THGs. But the probability is that it's ERE, not EIR.
Yeah.
The longer the sentence, the more likely you're
Yeah, that's true.
But then, are you kind of talking about the actual way you say it, like the way you say the word as well? So is that the hidden bit? So the actual intonation, or
the actual things you're saying in the hidden states. So basically, what's in your mind is the hidden states. What I got is the visible states.
Yeah.
Or the
doesn't take inflection.
the sound. Yeah.
It's really interesting. That's what I'm asking.
But I think it would take inflection into account.
It should do, if it's sound, isn't it? Yeah.
If you take inflection into account, the spelling part is much more difficult because often when you do audio analysis, you break it down into phonetic sounds and then you use those to make up the words. Yeah. If a word with different spellings have the same phonetic pronunciation, you have to use a different system.
That's what I was saying before about actually the difference if you're writing it as opposed to speaking it, because maybe when you're writing it, you actually get it wrong. So you've actually now given it an incorrect thing because your English is very good.
Because that's exactly the example. So in this evaluation, say if you spelled something wrong, and according to the hidden Markov model you got previously, you got very small chance to write that way. So you can just promote, did you write it wrong?
So with that, Microsoft Word, for example, going and doing a spell check, is that as clever enough as, is that how they do it? Or what's their kind of, I can imagine not. But.
Code, you can see
So
it.
I can't say that for sure, but I'd say more than 80% of all the speech recognition, writing recognition are based on this.
Cool.
So very likely that you're using it. But also, they try to do a lot of pre-processing. So, for example, the voice recognition, you don't just feed the system with the voice, but you do pre-processing to, so for example, chop every one word to different vowels.
Yeah.
And do some abstraction of that, take out features, then you feed this model.
That makes sense.
I think there's definitely something similar to this, guess what I think the next one is.
Yeah.
Right, I can just go, yeah. It's like about 10 words in low, and it's like, I didn't know that.
That's quite cool.
And you see that.
Yeah, I guess so. Well, this is really techie details, so I don't have to go to the very details, but basically the fact that you can, to find out the best way, you don't have to calculate all the paths. And instead, you can just calculate the path. So if you go it from backwards, you just always calculate the path that gives you the best probability by buffering all the rest information. That is just similar to the previous question. So instead we buffer the sum of the previous states here, we buffer the maximized value here. That just gives you the right path. Yeah, one, again, it's detailed problem. So we are calculating the probability is always less than 1, and because you are calculating like thousands or 10,000s of words, so that just decreases exponentially, and the float just can't hold that. So instead we calculate the multiplication, we calculate the logarithm. The very last question is learning, because in many situations you don't really have the hidden Markov model. That is very abstract problems. So you are trying to build your own hidden Markov model. If I still use a dice problem to do the analogy, is you don't know like what's the probability for me to pick up the next die, because I don't know that there's no such a number. But I can just throw the die and pick the die like thousands of times and record it, build up one model that might fit me, and say Pete, throw the die again, and build a model for him. So the next time when we see a sequence, we can figure out which model just fits that the best. There might not be a perfect model, but as long as you can tell one from the other, that is good enough. Yeah, so this will be basically in mathematical way, it's more complicated. We are doing that in using expectation maximization algorithm. So basically, you don't have the parameters in the model. You start by some random initial numbers. You feed the model. You do the evaluation. You calculate the error, and then you update the parameters to try to achieve the best one. And it's only stopped when it converges. So if you're interested, so the name of the algorithm is called Bob Welch. Yeah, thanks. I thought I read that.
So the book is okay. I'd like to get I was clever enough. It looks like a Bob Welch. So Bob
Welch algorithm, and it's one kind of expectation maximization algorithm. So that is 2 parameters you involved. That is not the hidden Markov model, but it's like the buffer parameters you used well, this one is to compute the probability to go past one state. So what's the probability you can go past this state? And this is, well, given this state and that state, what's the probability you can go like past that 2 states? And then you try to maximize that numbers iteratively. Yeah, so that was the mathematical way of explaining the hidden Markov model. And why are we building that in LabVIEW? Well, there are a lot of libraries there already for hidden Markov model in R, Python, C, C++, Java, MATLAB, and so on. I haven't seen one in LabVIEW, and since people are using LabVIEW for different cases, sometimes you don't want really like mix the language if you don't have to. So besides building some other machine learning toolkits, I found this one might be useful, and yeah, and when I Googled it, also someone in my forum asking if there is such a toolkit. Yeah, so the way I built that, I didn't use third-party add-ons in LabVIEW. So you install LabVIEW, and that's all you need. You don't need to download some other add-ons to do that. I put in the equations, so in case you want to check the implementation or you want to do the coding in a more effective way, there are materials there. So I created a LabVIEW library, and here you can see that is API. So that is the method you're calling to address that three problems. So there is forward and backwards algorithm to solve the evaluation problem, and the B2B algorithm to solve the decoding problem, and the Baum-Welch algorithm to solve the learning problem. And there are also sub-VIs, so all the details are wrapped in the sub-VIs. It's not exposed, but if you are interested, you can look into it. And I also created some demos for the method, so you can try the comparative method with whether some previous result you got, or with your own method. And that is the front panel of one demo. I will go to more details for the next slides. So that is the example of Baum-Welch algorithm. So the detailed algorithm is wrapped up and documented. If you want to dig into it, the equations are there, and you can check that and try to, probably there is a better way to compute the multiplication of 2D array and 1D array. You can always try to optimize that. Now is a demo. I try to find out a more intuitive way to demonstrate this, but yeah, let's see. So the input is one paragraph, or there are about 5,000 words. 5,000 letters in that paragraph. I just took it randomly from online, and that is the statistic of the letters. 0 is space and start from A to Z. So you can see some of the letters just occur more frequently than the others. And if we feed that, so now we don't have a hidden Markov model. We don't know how letters are connected to each other. So we don't have that prior knowledge. And we just define the hidden Markov model, say there might be two hidden states. And we can see the letters, but can you just sort it to two states, two hidden states? So initially, we tell there are two states. So one state is the red dot, another is the blue lines. And we just initialize them evenly. It's not really 1/27. There's slightly a small randomness, which you can't really see.
So what do you mean by this? So in this example, the two states would be what? Which letter comes before the next letter? Or
no, say we just assume there are two states. That some of the letters more likely to belong to this state.
So in terms of state, it's part of the word, or?
One group.
So paragraph group, wording group.
You won't see paragraph. It will only see the letters.
Yeah.
So
group will be a word.
No, two groups. Actually, there's the answers on the next next slide. So, but we say there are. But yeah, assume that you don't know English. You don't know, or that is not English, and you've just seen a lot of symbols. And firstly, you want just to try to sort it to different ones. Say that this one or this are more meaningful to each other, or they are more related to each other, and if the other one appears, it's more likely to belong to the other group. So that's like the way you analyze something. You have no prior knowledge. Yeah, so after we do the hidden Markov model, and that is emission matrix. So that is, say we have two. That is like two dies, right? So for one die, it's more like to have some. Sorry, are you?
Yeah, bro, I was wondering, are you just sorting the vowels from the consonants? Basically, one group of letters is the vowels, which are more frequent, and then the other group turns out to be the consonants, which are less frequent. Is that what happens there? The red dots are the vowels?
You just give up. You just give away the best bit. Yeah. I mean to say, ta-da. Yeah.
That was well explained. So.
Yeah, because I suppose like what makes it is that so each one knows the letter, what's the next or nearest letter to it in each time. So in a word, you can kind of have a vowel next to a consonant, which is kind of like.
Yeah, so yeah, exactly. So these red dots are A, E, I, O, U, and the blue lines are the consonants.
This should define the Scrabble board really, and the point system.
Oh yes, definitely. Yeah.
And also, if we go back and see that A, E, I, like I, O, U. Okay, A, E, I, O, U. Well, they don't really just stand out right there, right? Something like, which is this one? T. Well, yes, some methods. And two of this, right? They're just more. They appear more frequent than the others, like S and T. They appear very frequent. So. Yeah, so they don't just do that according to statistically, but like the relationship between the letters, and it just come out to be the vowels and the consonants. Yeah, so now we have the vowels and consonants. So imagine that is another unknown language, and you're trying to figure out like that is like very alien language or a very old language. You have no real knowledge. Now you can tell that that kind of symbol belongs to vowel. If there is such a vowel, that is one thing. That is another thing. Yeah. So you can find this toolkit from Austin Consultants blog, or if you Google Hidden Markov Model LabVIEW. So the first result is from online forum, but the second result is the Austin Consultants blog. And yeah, your feedback is welcome, because at the moment the computation is not run like in a very effective way, and you are welcome to improve the speed. Yeah, thanks.